Good morning. I hope you all had a wonderful 3-day weekend. Cool to have you here. Let's just start taking care of business. Okay, so for those of you in section 01, I've got some piles going down there of the QA1 lab and exam prep 2. So thank you for turning those in. And then for those of you in section 01, we will take the midterm next Monday. That'll be the big thing we'll do. Midterm 2 is what we're going over right now in these notes. It's basically over problem set 4 and 5. So thermodynamics, delta G, delta H, delta S, as well as solubility, KSP stuff, formation constants, electrochemistry, jazz like that. There's a sample midterm you can check out. Definitely see that. Should be chill. 20 multiple choice questions. Same format as exam 1. Those of you in H1, today's the day we'll take the midterm. And then next Wednesday, we will have QA3 lab. Section 01 will do QA3 lab after. QA3 lab is a lab you'll turn in before you leave. So if you want to, you should definitely look at like the post-lab questions before you come to lab, because that's one less thing you have to scramble with at the end before you do. And just like QA1, post-lab questions, pretty chill, look on the front page. All right, shouldn't be a big deal. For those of you in section 01, on Monday of next week, again, we'll take midterm 2, we'll do QA3 lab. And while you're there, I will give you a copy of take-home quiz number 6, because a week from today, which is Wednesday, 9 a.m., that's when exam prep 3 will be due, problem set 6, which you can just look at the video. We're not going to go over in class. And then this take-home quiz number 6. And I don't think take-home quiz number 6 will be too crazy. So it's just kind of finishing up the term, just like that. Section H1, when you come to lab next Wednesday, you will turn in take-home quiz 6, problem set 6, and the final exam prep. So we're getting down there, all right? Definitely some weirdness because of Memorial Day. Any questions on anything? Cool. And also for my video viewing audience, I am trying a new format today. We'll see if it works out and stuff. Any feedback, I'd appreciate it. I had an idea over the weekend I wanted to try, so we'll check this out. Take care of business. Cool. So let's continue on with the review we've been doing the last couple of days. These will be mostly over electrochemistry kind of questions. Check it out. So the first question here is to balance this reaction in base. And when you balance redox reactions, it does make a difference if you're in acid or base. So this one is in base. Remember, pH is greater than 7 are basic, so this is a base one. So see if you can figure out which of these would be the best answer here for this question. And I'll give you a couple minutes to work on it, and then we'll talk about the answer, stuff like that. Okay, so as we talked about in lecture, there's two ways to do redox reactions in base. You can right away balance them with hydroxide and water. So hydroxide has a bigger, like 1-to-1 oxygen to hydrogen, so you add the hydroxide to the oxygen side. And water with 2 H's per 1 O, you would add this to the hydrogen deficient side. And if you can do that, and I'll try and show you an example of that here in a second, that is a faster method. But in my world, it's almost easier to balance first in acid, which I find relatively easy, and then neutralize in base. So on either way you do it, what you want to do is you first want to separate out the similar species. So I would separate out permanganate and MnO2, and an iodide and iodine. Now iodide and iodine are pretty easy because there's no oxygen or hydrogen. But permanganate and MnO2, they do have oxygen. So you can see that this side is missing some oxygen, so we want to add some hydroxide. And what I always want to do is I want to add 2 hydroxide because that would balance the oxygen. But because water's on the other side, what you almost have to do is add extra hydroxide. And if you do this, let's see if this will work out because I always get messed up here. Let's see. So then 2, okay, yeah. So you want to do this weird 2 to 2, anyway, it freaks me out, sorry. Anyway, if you add extra hydroxide, all right, so even though there's only 2 oxygens needed, if you add 2 extra here, then you've got 4 plus 2 oxygens, 6 total. And if you add 2 waters then to this side, 4 and 2, 6 oxygens. And then 2 would be 4 hydrogens, and that's what you have here. So this part always stepped me up and made me mess up on things, so that's why I don't use it. But if that's cool with you, it is a time saver, so you decide for yourself what is better. What I did, and what I'll show you in this example, is I did it first in acid. And acid means you can use H plus and water. So you separate out permanganate and the iodine from each other, all right? And like before, you want to have you need extra oxygen on the right. So initially it's just 2 waters, and then you'd have 4 H pluses on the right. But in the next step, you want to make sure that the electrons cancel, don't show any electrons. So initially this is a different reaction. You'll have a total of 6, and then the 6 you multiply this one by 3. So when you combine these all, then you don't have any electrons showing, all right? So this would be the reaction if it was balanced in acid, if the pH was less than 7. But we don't have a pH of 7, we have a pH which is greater than 7. So to go from here to the base version then, you have to add an equal number of hydroxides for every H plus. So in the next part, I'm going to add 8 OH minus to both sides. The 8 OH minus will cancel the 8 H plus. That'll make H water, 8 waters when all is said and done. But if you add 8 hydroxide here, you have to add it to this side as well. So, long story short, to get rid of the acid, you add an equal number of hydroxides. And 8 H plus and 8 OH minus make 8 waters. But if you add 8 hydroxide here, you have to add it to the other side, like in math. When you have 8 waters, you should check to see if there's any waters on the other side. This happens, and there are here. So these 4 waters go away, and you're left with 4 waters. So at the very end, this is the reaction you end up with. And again, either way you want to do this is fine. It is a little simpler to do the hydroxide water part directly. But if you're having issues, and I certainly do have issues with these, I almost always do it in acid first and then do it base. So find the way that works for you, okay? Any questions on that? Here's a question that shows several electrochemical cell potentials. And the question is here, what is the strongest reducing agent? Now, E cell values, we saw that as E gets positive, delta G gets negative. So strongest in electrocell potentials means the biggest, most positive E cell. But also remember here, we're looking for a reducing agent. So based on all those things, see if you can figure out which of those would be the best reducing agent in this list. We'll talk about it here in a little bit. Cool. All right, so in this list, the most positive value will be the strongest, all right? So as these are written, then you can see the positive 1.61 volts is bigger than all of them. So it might be tempting to think that that is the answer here. But remember, I'm just the messenger and I didn't make these rules. And there's a difference between something that's reduced and something that's a reducing agent. So if something is a reducing agent, are we looking for something that's being reduced or something that's being oxidized?
Oxidized.
Oxidized. Freaking electrochemists. No, I'm just joking. Now, these reactions here are all listed as reductions. All right, electrons are being gained by the reactant to make a product. And a reducing agent is a fancy way of saying, oh, we want something that's being oxidized. So all of these as reductions aren't really going to help us. We want the opposite. And so what that means here is that, for example, the last one, aluminum 3 plus and 3 electrons making aluminum, has an E cell of minus 1.66 volts. We want to flip all of these around. So aluminum is going to be losing electrons. It's going to create 3 electrons. What happens to the E cell value when you flip the reaction?
Positive.
Positive, that's right, change the sign. So it becomes positive 1.66 volts. So if you flip all of these around, those are the numbers you want to look like, not really the numbers as written. So because of that, answer D is the best answer here. Aluminum going to aluminum 3 plus is the best piece that's being oxidized. It's the best reducing agent here. So just be careful. And again, I didn't make these rules. I think they suck, to be totally honest. However, we got to deal with what we got. And aluminum is going to be the best answer here. Reducing agent equals oxidized. Oxidizing agent equals reduced. Any questions on that? So the next question is what will happen kind of question. And we want to know in this question if tin will reduce silver plus to silver. And you have those values right there. And the answers are yes, no, only if it feels like it is not a real answer. So you don't put that down. But anyway, see if you can figure out if this is going to happen, yes or no. if you see a question that says, will this happen? Is it going to occur? These kind of things. Those are all questions about spontaneity. And really, spontaneity is delta G. So if a reaction is spontaneous, it's going to have a negative delta G. And as we've seen earlier in lectures, delta G equals minus NFE. And why this is relevant, if E is positive, a positive times Faraday, which is positive, times moles of electrons, which is positive, times negative 1, that's going to give you a negative delta G. So positive E's correspond with negative delta G's. So if this reaction comes out to be positive for E cell, we're going to be good to go. So this question is saying, will tin plus silver plus make silver, and as it turns out, tin 2 plus? So again, like most of these reactions that are listed as reductions, we're going to need to flip one of them. And we want tin as a reactant, not tin as a product. So we're going to flip that second reaction around, make it positive 0.14 volts. We're going to leave silver just as it is, which is already positive. So two positive numbers together, it's going to happen. It's going to be positive. How much is it going to happen, Dr. Russell? Good question, random student in the back of the room. You can actually figure out the E cell values, all right? So this is balancing the reaction. Can't show the electrons in my world, so we'll multiply the silver through by 2, but that doesn't change E cell. Still going to get positive 0.94. This is the reaction that will occur. And because, again, that E cell is positive, delta G is going to be negative. This is going to happen. If it was a negative E, then it would not happen. All right, that's kind of the thing. So. Questions? All right. This is a question when you can take an E cell value and turn it into delta G probably first, and from there turn it into an equilibrium constant K. You can also go direct from the E cell value to K if you want. Either way, see if you can figure out what the value of the equilibrium constant K is for this reaction. Play with this and we'll talk about it here in a little bit. Cool. All right, so in the last one, we saw that delta G equals minus NFE. Delta G also equals minus RT natural log of K. And K are all the equilibrium constants we've seen so far. So KAs, KFs, blah, blah, blah. The important thing for us is that a lot of times people want to know if something's going to happen, if it's going to be spontaneous. And as we talked about, delta G has to be negative for spontaneous reactions, and that corresponds to positive E. Well, with equilibrium constants, that's going to correspond to a K greater than 1. So if something's going to happen, it's going to have a negative E, delta G, a positive E if it's a redox reaction, and a greater than 1 K value. So in this version, we have an E value which is positive, all right? And if E is positive, that corresponds to negative delta G, but more importantly for us, it corresponds to a K which is greater than 1. So if you look at these answers, it's not going to be A because that K is less than 1. It's not going to be D because that K is less than 1. And equilibrium constants are never negative, so E is just silly, all right? So it's going to be B or C. That's kind of what it comes down to. And to knock this out, you want to solve for K. N, F, E, and RT are all things you need. So there's different ways to figure out the N, the moles of electrons. But what I would do is like 2 iodides are going to iodine. And the only way that's going to happen is if 2 electrons are removed from iodide. You can also see the 2, which is what N is going to be, using the chlorine, because chlorine going to chloride, this has no charge, this has 2 times minus 1 minus 2 charge. So the chlorine has to accept 2 electrons to make that process happen. So I use like 1, either the reduced part or the oxidized part, doesn't matter. N is going to be 2. Is that cool? Any questions on that? Okay. F is just something you need to know, 96,045 coulombs per mole electrons. That's the Faraday constant. That's the thing you should know for the midterm. E cell is given, 0.825. R is the energy R, 8.3145. T is the Kelvin temperature, so 25 Celsius would be 298. So you plug all that stuff in there, that equals natural log of K, and to get rid of the natural log, you take the anti-natural log, that little e to the x button to figure it out. If you got answer C, taking care of business. Any questions on that? So just make sure you know Faraday, make sure you know the energy R. You might need both of those and stuff this week or next Monday. Questions? Cool. Okay, here's a problem. We're creating a voltaic cell. Now, voltaic and galvanic means that the overall E cell value is going to be positive. Voltaic and galvanic means that something happens. It's an active battery. So remember that in the back of your mind. And we're using it in Alaska. The average temperature is 5 degrees Celsius, so it's colder than usual. And we want to calculate the expected cell potential under these conditions. Now, this one, when you see weird temperatures and you see weird concentrations, this is going to be a Nernst equation problem. And E equals E0 minus RT over NF, natural log of Q. You can use these two values to find the voltaic value, which has to be positive, all right? That's going to be E0. RT, NF are mostly constants, but remember temperature here is 5 Celsius, which would be 278 Kelvin. Q will be products over reactants. And you can use the concentrations that are listed there to try and figure out here how this all works out. So see what you can do with this problem. We'll talk about it here in a little bit. Okay, so voltaic and galvanic means product favored, spontaneous, a battery that works, okay? And as we talked about, you need to have a positive E cell value if the reaction's gonna happen. So some of you might be able to look at those two reductions. You have to flip one of them, and it makes sense to flip the second one, because that would be then a positive 1.66 volts, and you add it to the minus 0.25, you're going to get a positive number. But if you don't see it, there's another way to figure this out too, because this is the shorthand notation for these E cells, electrochemical cells, and electrons always flow from the left to the right. So what this is saying then is that aluminum is going to aluminum 3+, and the electrons get kicked out after that. This is the phase boundary between the two cells. And on the other side then, you have nickel 2+, and it's going to nickel. And so if you realize this is positive 2, this doesn't have a charge, you're going to have to add 2 electrons to that side to make that balanced. So the aluminum is being oxidized and the nickel is being reduced. So we're going to flip the aluminum then definitely, make it a positive 1.66 volts. We'll then subtract the 0.25 volts because we haven't changed that. And then the overall cell, I think it comes out to be positive 1.41 volts. And this is E naught. This is the value that goes right there, okay? But we need to go a little further in this problem. I'll talk about why. So if we're gonna balance this reaction, we need to make sure the electrons cancel. I'm gonna multiply the first reaction through by 2, so 2 times 3 is 6 electrons. And I'll multiply the second reaction through by 3, because 3 times 2 is 6 electrons. So when all is said and done then, 2 ALs and 3 nickel 2 pluses goes to 2 aluminum 3+ and 3 nickels. That's the balanced reaction. And we're using that, we're doing this for 2 reasons. First of all, 3 times 2 or 2 times 3, 6, that's N. That's the number of electrons transferred. So N in this case is going to be 6. But the other reason why we need this, Q is the reaction quotient, products over reactants. Now, the nickel and the aluminum are solid, so we don't care about those. But Q, definitely, we need to put in all of the aqueous species. So Q, products over reactants, Q is going to be aluminum 3 plus squared, and we're going to use the number that's next to the aluminum for that. And in the denominator, we're going to put the nickel 2 plus value to the third power. So for all of these reasons, you need a balanced E reaction. You can use that for the Q, and also you can find the number of electrons in it. Any questions on that? Okay, so you can calculate Q, or technically, you can calculate E naught by putting these two together. R, 8.3145, temperature, 5 degrees in Kelvin, 273 plus 5 is 278.15. N, we just saw was 6 moles, all right, because 3 times 2 and 2 times 3, that's the moles of electrons needed to basically not show up. F, 96,485 coulombs per mole electrons. And now Q, products, the aluminum 3 plus to the second power, divided by nickel 2 plus to the third power. And the aluminum here is 0.001, so 10. So that's 0.0010 squared divided by 0.50 to the third power. So you throw all that into your calculator, 1.46 volts is what you should end up with. So there's a lot of little pieces, but it's all stuff we've done before. It's just figuring out how they all go together, jazz like that. Nernst equation, it's just kind of annoying, but I don't think it's like necessarily hard. It's just kind of frustrating and stuff sometimes. But if you look at all these things, you should be good to go. Any questions? Cool. So again, another use of the Faraday constant, another use of the energy R, so make sure you have all those values and stuff taken care of. Cool. Okay. This last question is a question on what's called quantitative electrochemistry. In the last reaction, aluminum will react with nickel 2 plus to make aluminum 3 plus and nickel. That's a reaction. You put this stuff together and it just starts reacting. This is an example of a reaction that won't automatically happen. And we're trying to make gold 3 plus ions turn into gold. And that's not a preferred reaction. However, if you apply electricity from another source, like an outlet or anything like that, you can make things that aren't thermodynamically favored happen. And that's how a lot of metals are made and non-metals and stuff like that. So on these problems, a couple of hints. First of all, amps, which are used for electricity. An amp is a coulomb per second. So when you see amp, just cross it out and put coulombs per second. And if you combine that with the Faraday, 96,485 coulombs per mole of electrons, you can have a conversion there where getting rid of coulombs is cool. So anyway, we want to know in this question how long it's going to take to have a 2 amp current convert 0.0100 moles of gold 3 plus into gold. So see if you can figure that out. We'll talk about it here in a little bit. Cool. So these kind of questions, they either give you time and then it wants to know like an amount, like moles or grams, or in this case, you're starting with an amount and you want to know the time elapsed. So this is one of the time questions, but it's a similar process if you have to find amount. So in this problem, I would start with 0.0100 moles of gold. And I need to figure out how many moles of electrons we need. And to figure that out, we're going from gold 3 plus to gold 0, all right? So how many electrons would you need to turn one gold 3 plus into one gold? 3, that's right. So you'll take the moles of gold 3 plus and multiply by 3. That's 3 moles of electrons per mole of gold 3 plus, something like that. Then you can use Faraday constant because that's got moles of electrons in the denominator. So you multiply moles of electrons by Faraday to get the coulombs, and then amps is coulombs per second. So you want to essentially divide by the number of amps, the number of coulombs per second, and that'll push time to the top. And if you do all that, if you got 1450, pat yourself on the back. So here's the amount, gold. We need 3 moles of electrons to turn gold 3 plus into gold. Multiply it by the Faraday to get the coulombs, and then you want to divide by the coulombs per second to get just the seconds. So this is going to take 1450 seconds. Now, if this was a time problem and it wanted to give you amount, you would just do the opposite. So you'd start with time, you'd multiply by the amps, you'd divide by the Faraday, et cetera, et cetera. But it's the same kind of process, just going back and forth. And if you're making like aluminum metal, this is something that you would probably have to figure out once in a while. Questions on that? Fantastic. All right, so that's it of our exam review. We'll either take the midterm today or next week, Monday. If you have any questions on anything, let me know. We'll start talking about coordination chemicals on Friday. That's right, today's Wednesday. All right, Friday. So we'll see you on Friday. Have a great day. Thanks for being here.